Hey guys, this video is about the common ion effect and buffer solutions. So let's start with the common ion effect. Now this is really just Le Chatelier's principle, but we're going to quantify it here and sort of justify, I guess, part of Le Chatelier's principle. Remember, Le Chatelier's principle says that when you disturb an equilibrium, the equilibrium adjusts itself so as to come back to equilibrium. So in other words, if you add a reactant, it shifts to the right. If you add a product, it shifts to the left. And remove a reactant, it shifts to the left. Remove a product, it shifts to the right. So let's look at that. So we're going to look at a solution of a weak acid, hydrofluoric acid, 675 mils of a 0.25 millimolar hydrofluoric acid solution. And we're going to find the pH. Okay, so this is the equilibrium. This is our ice table. The Ka for for hydrofluoric acid is given 7.2 times 10 to the minus fourth. So our typical ice table, set up our equilibrium expression, and at this point you can probably just skip the ice table because it's a simple one, and just go right to x squared over 0.259 minus x equals Ka. But if you're uncomfortable at all doing that, just set up the ice table. Just takes a minute or two. Anyway, so solving for x, which is the concentration of hydrogen ion, we get this. Now, I solved the quadratic. We could have neglected x and we would have gotten something really close, 0.0136, and we would have rounded a little differently. But it's simple, so I just solved it. And so, because now we know x, which is the concentration of hydrogen ion at equilibrium, we can find the pH, which is negative log base 10 of the hydrogen ion concentration, and we see that the pH is 1.88. All right, so nothing new so far. Okay, we've done that a few times now. Now we're going to disturb the equilibrium by adding some potassium fluoride. Now, we don't care about the potassium. It's a spectator ion, and it's there because you can't buy a bottle of fluoride ions because they would all have negative charges and repel each other, so you need a counter ion. But it's soluble. Again, going back to our solubility rules from Chem 101, we see that potassium fluoride is soluble, which, by the way, we're going to do a lot better than just the solubility rules in the next module. But so what we do is first figure out the concentration of fluoride ion, which comes from the potassium fluoride that's been added. So we take the mass of potassium fluoride, divide by its molar mass, gives us moles of potassium fluoride, which is the same as moles of fluoride ion because there's one fluoride and one potassium fluoride. And we divide by the volume, it was still 675 mils, and we get the concentration of fluoride ion. So now we set up our ice table. So at this point, I would definitely recommend using the full ice table. And so what we have here is initially the concentration of the hydrofluoric acid is going to be the initial concentration that we had before minus our x that we solved for in the previous problem, right? So, if you remember at the end of our ice table, we said that the concentration of hydrofluoric acid at equilibrium before we added the potassium fluoride was 0.259 minus x, and that's the x that we found, and so it's 0.2457 molar. The concentration of fluoride ion in our initial concentration in this problem is going to be our x plus the amount of fluoride that we added. So if you remember back to the previous problem, at the end of that problem, the concentration of fluoride at equilibrium was x, which is this number right here. We added this much from the potassium fluoride, so now we have this much fluoride ion initially. And our concentration of hydrogen ion, that's just our x from our previous problem. So these are now our initial concentrations. They were our equilibrium concentrations before, but now that we're disturbing the equilibrium, these become our initial concentrations. And so we know that, okay, so here's where Le Chatelier's principle is still useful. We know, guys, that the equilibrium is going to shift back to the left because we've added a product. We added fluoride ion, so we know it's going to shift that way. And that right there, guys, that tells us why it's negative x for the fluoride and hydrogen ion and plus x for the hydrofluoric acid instead of the other way around. Okay, so we put those in, and we have at equilibrium our concentrations in terms of our initial concentrations here and x plus x or minus x. And so our Ka, same Ka, looks like this now. So now at this point, the thing to do probably is just solve for x. You're going to see, by the way, where you don't have to go through all this. There's a much easier method for doing this problem under certain conditions, which we'll get to. But anyway, solving for x, we get 0.0119. It certainly is not less than 5% of 0.133, so we couldn't neglect it here. And it's not 5% less than this, so we'd have to, if we wanted to try an assumption, we couldn't neglect it up here. Maybe probably down here. It's less than 5% of this, I believe. But and that would make our life, at least quadratic, easier. But we just solved it, and we have our new x, right? So at equilibrium, remember, we want to find the pH. That's our goal. You'll see why in a minute. So our hydrogen ion concentration is going to be 0.0133 minus x. This is our x. So we get the hydrogen ion concentration of 0.0013. And that means pH, which is the negative log base 10 of the hydrogen ion concentration, will be about 2.9. That's significantly different than what we got before, which was 1.88. So, and that makes sense. You should always check right and see if it makes sense, because we added a base. Remember, the conjugate base of a weak acid is still a decent strength base. It's a base, and when we add a base, we expect the pH to go up, and it did. Went up about a full pH point. All right, so that's the common ion effect. But what we've done here that's different than Le Chatelier's principle is we were able to calculate concentrations of everything now at equilibrium when we do add a common ion. That's what's different. So now let's look at buffers, which is related to what we were just talking about. So first of all, what is a buffer solution? A buffer solution is a solution that consists of a weak acid and a salt of its conjugate base. Or that's how you make it up. There's a lot in buffer chemistry, and there's different ways to make up buffers, but at this point, this is what we're going to do. So, for example, acetic acid, which is what this is a weak acid. When I say salt of its conjugate base, that just means it's conjugate base with a cation, right? A metal cation. I chose sodium, could have been potassium, or any other, it has to be soluble, any other soluble cation here that would neutralize the charge. So this is sodium acetate, and so if we put some acetic acid and added some sodium acetate to it, we would have a buffer solution. Or we could also make it up by taking a weak base and a salt of its conjugate acid. So ammonia is a weak base. Its conjugate acid would be the ammonium ion, NH4+, and its salt now would be an anion added to that. So I chose chloride. It didn't have to be chloride. Could have been nitrate, something soluble. So what a pH buffer does, and buffers are really useful solutions. For example, your blood in your body is a buffer system. If it weren't, we'd have a hard time surviving. So what a buffer does is it resists a change in pH when an acid or a base is added to that buffer solution up to a point. That point is called its buffer capacity, which we'll investigate in just a minute here. But once we exceed the buffer capacity, and then it's not a buffer solution anymore. Basically, we've used up all of either the weak acid or its conjugate base. But up until that point, you'll see the pH changes. I mean, it changes, but very little, much different than if it wasn't the buffer solution. So let's look at a solution. So we're going to have 750 mils of a buffer solution. And we're going to make it to be 1.25 molar acetic acid and 1.25 molar sodium acetate. So there's a weak acid and a salt of its conjugate base. And we're given the Ka for acetic acid, 1.76 times 10 to the minus fourth. And so the solution, okay, this is our beaker over here, right? These are the species that are going to be present, other than water, of course. Sodium acetate breaks apart into sodium ion and acetate ion. We don't care about the sodium ion, it's the spectator ion. We're going to have the acetate ion, we're going to have acetic acid, and once we come to equilibrium, we're also going to have some hydrogen ion. And so let's look at the pH of this system right here. So we're going to set up our ice table. Here's our initial concentrations, and no hydrogen ion to begin with. Just a side note, guys, There actually is some hydrogen ion constant in that solution that comes from the auto ionization of water, but it's about, at 25 Celsius, it's going to be about 1 times 10 to the minus 7th, which is negligible compared to these numbers here, so we don't worry about it. So anyway, set up our ice table. Because this is 0, Q is equal to 0, it's going to shift to the right. Negative x, and so we get our equilibrium expression. Now, if we neglect x compared to 1.25, this is really nice. It becomes real easy to solve because if this x here and this x here are neglected, the 1.25s end up canceling each other out, and we get x equals 1.76 times 10 to the minus 5th, which, don't even have to do any algebra to solve for. And so that's, first of all, was that a good assumption? Absolutely. 1.7 times 10 to the minus 1.76 times 10 to the minus 5th is definitely a lot less than 5% of 1.25, a lot less. So it's a good assumption. So now that we know x, we know the hydrogen ion concentration, and we can get the pH, negative log base 10 of the hydrogen ion concentration, which gives us a pH of 4.754 or so. Now let's look at what happens to this buffer solution when we add an acid, a strong acid. So we're going to add some 6 molar hydrochloric acid, 25 mils of it, okay? So the first thing we're going to need to do, which we won't always have to do, there's going to be an easier way to do this stuff. But the first thing we're going to do is calculate the initial concentrations of everything before the new equilibrium is established using the dilution equation. Because when we added that 25 mils, we changed the volume of the solution, so the concentrations of everything changed. So our new, C1 V1 equals C2 V2, right? The dilution equation. Solving for C2, we get C1 V1 over V2. Because we started with the same initial concentrations of acetic acid and sodium acetate, this calculation will be the same for both of those. 1.25 molar times the initial, C1 V1 over C2 is, V2 is 775. That's just our 750 plus 25, 775. And so we get 1.21 molar for both acetic acid and sodium acetate. Hydrochloric acid is also diluted. When we added that 25 mils of the 6 molar hydrochloric, it was diluted to 775 mils. So there's our V2, V1, C1, and we get 0.194 molar or so for the hydrochloric acid. Now what we do, okay, the way to think about this, whenever you have an acid and a base, they react with each other. Okay? When you add an acid to a base or you add a base to an acid, they react. Because we're adding an acid, the hydrogen ion, we don't care about, by the way, the chloride ion. Remember, hydrochloric acid is a strong acid, completely dissociates in water into the hydrogen ion and chloride ion. Chloride ion is the spectrate ion. We don't care about it, just the hydrogen ion. So the hydrogen ion will react with the base, in this case the acetate ion, to form acetic acid. Notice the single arrow, okay? And when we do that, we take away, okay, so we had 0.194 molar hydrochloric acid or hydrogen ion, so we take that much acetate away, so our new initial concentration of acetate will be our initial 1.209 molar minus the amount that reacted with the acid right here. Gives us about 1.02 molar or so. And we're making acetic acid. So for every proton that we add from the hydrochloric acid, we make a molecule of acetic acid. So initially we had 1.209 molar acetic acid. We made 0.1935 molar more, and so now we have 1.403 molar acetic acid. So now we can set up our ice table. Initial, 0. We've used up at this point, the way we think about it is all the hydrogen ion has been used up, and we're going to make some more in a minute once this equilibrium reestablishes itself. But so here we go. This is supposed to be plus, not 1. I guess plus 1 or minus rather. So minus x plus x plus x. And then we set up our equilibrium expression. Once more, if we neglect x compared to, if it's a lot less than 1.016, it's certainly a lot less than 1.403, which is bigger than 1.016. So we neglect x, and we get x is equal to 2.43 times 10 to the minus 5th, which, yes, that was definitely a lot less than 5% of either of these numbers, so it's a good assumption. So now that we know x, we know our hydrogen ion concentration, pH, negative log base 10 of the hydrogen ion concentration, 4.614. So remember, our pH of our original buffer solution was 4.754. It went down to 4.614. So it did go down a little bit. Got more acidic because we added an acid, but not very much. It kept it pretty stable. That's not a very big difference. Let's look at what would have happened if we added that exact same hydrochloric acid, 25 mils of 6.0 molar hydrochloric acid to 750 mils of just water instead of the buffer solution. Well, then the hydrogen ion concentration will be what we calculated earlier, 0.1935 molar. So that means the pH would be negative log base 10 of that, which is a point, less than 1, really acidic solution, way different than 4.614. So our buffer solution did its job. It resisted a change in pH when we added an acid. And the same thing would have happened if we had added a strong base too. pH would have gone up, but only by a small amount. But once we exceed the buffer capacity, we talked about this a minute ago, the solution will no longer be a buffer, because if we add more acid than there is of the weak base, so in our buffer solution before with acetic acid and acetate, if we add more moles of our hydrochloric acid or whatever the acid is, then we have moles of acetate, then once we've reached that limit, once we've used up all the acetate, now it's not a buffer solution anymore. And the pH at that point will be determined solely by the excess acid, or if we're adding a base, by the excess base. Let's look at that. So let's say we added 160 mils instead of 25 mils of 6 molar sodium hydroxide to our original buffer solution, 750 mils of 1.25 molar acetic acid and 1.25 molar sodium acetate. So let me go look at that. So we're going to find out how many moles of everything we have. So 160 mils or 0.160 liters times 6 moles per liter is this many moles of sodium hydroxide, this many moles of acetic acid, this many moles of sodium acetate or acetate ion. So the way I set this up is we've added, more sodium hydroxide than we have of in this case, the acid, because this is the base. It's going to interact with the acid. And so what happens is, kind of like we saw before, in this case, the base, the hydroxide, will react with the acid part of the buffer solution, single arrow, it's 1-to-1, right? So for every 1 hydroxide we use up 1 acetic acid. Well, we only had 0.9375 moles of acetic acid. So we're going to use up that much of the acetic acid. And make, there's water and acetate ion. And so now at this point in the solution, we have, so we made this many moles of the acetate ion. So initially we had that many moles of the acetate ion. So now we have 1.875 moles of acetate. We've used up this many moles of the hydroxide. Once we ran out of the acetic acid, then the hydroxide doesn't react anymore. And we have this many moles, 0.0225 moles of hydroxide left. And we don't have any acetic acid left, 0. Now, small point. Okay, we're adding some water from the reaction. This will change the volume. It ends up, depending upon the temperature, this much water adds about 16 or 17 milliliters to the volume of the solution. But it's not necessary for our demonstration here to take that into account. Although, if we were really concerned about the actual amounts of stuff in here, we would have to take that into account. So the pH at this point is determined only by, in this case, the hydroxide, or if we had added an acid, the hydrogen ion concentration. It's excess. It's still in the solution that hasn't reacted. But what I'm going to do here is we're going to go through the whole ice table calculation and show you why you don't have to do this. So what I'm about to show you here is why you don't have to do what we're about to do. So our initial concentration of acetate is the moles over the liters. So we added 160 to 750, so 0.910 liters. So this many moles per liter. Hydroxide, this many moles that didn't react divided by the volume, that's our molarity. And we don't have any, at this point, before we reestablish equilibrium, we don't have any acetic acid. So 0. Q is 0. It's going to shift to the right, plus x minus x, and we get our equilibrium expression. Now this, guys, This is a base that's reacting. This is the reaction that happens. Remember, we don't have any, initially, you don't have any of this, right? So that's not going to, there's nothing for that to react with. What's going to happen is the acetate ion will react with water, accept a proton, make acetic acid and hydroxide. And so that means we need Kb. But that's easy. We know Ka. So Kb is just Kw over K. Kb is just Kw over Ka. Ka times Kb equals Kw. We saw that in an earlier video. Anyway, so there's our Kb, which is the K that's relevant to this reaction right here. And so plugging our numbers in here, neglecting x compared to 0.025 or so, we get that x is equal to 4.73 times 10 to the minus 8th. First of all, yes, that was definitely a good assumption. 4.7 times 10 to the minus 8th is a lot less than 5% of 0.0247 and certainly than 2.060. So now that we know x, remember x here is, well, to get the hydroxide, we want the pH. So to get the hydroxide ion concentration, we add that to our excess hydroxide, right? But look how small x is. When we add our x to our initial concentration of hydroxide, it doesn't change. I mean, any change is way down in the insignificant figures. And this is why we don't have to do all this. This is proving that we don't have to do all this. The hydroxide ion basically concentration did not change. And so the pH is just determined by the negative, pOH rather, is negative log of the concentration of hydroxide, which we could have just used this number here without using the ice table and all that to find. And so the pOH is 1.61 or so, pH is 14 minus that, so 12.31. It definitely shot way up. It's very basic. This is not a buffer solution anymore. This pH shot way up when we added our hydroxide, the excess hydroxide. So the takeaway from this, guys, is that once you've exceeded the buffer capacity of a buffer solution, the pH is determined solely by the concentration of either the excess acid or base, depending upon what you added. Now let's look at a generic sulfur. No, not a sulfur solution, it's a buffer solution, although some might say it's a sulfur solution, but it's not really. Made up of, our generic weak acid and its conjugate base. So there's our equilibrium. The acid in equilibrium with the hydrogen ion and its conjugate base. Ka looks like this. Now what I've done is that's actually parentheses around this, but this is the initial, I've written the equilibrium concentration of the conjugate base and the acid, weak acid, in terms of x, plus x here, and minus x over here. Or it could be minus x plus x, depending upon the concentrations, but it doesn't, you'll see it doesn't matter. Now if we take the negative log of both sides of this equation, okay, negative log base 10 of Ka is pKa, and using the properties of logs, we can rearrange this a little bit and get the negative log base 10 of the hydrogen ion concentration, which is the pH, then minus the log base 10 of everything else here. So now if x is a lot less than the initial concentration of the base, the weak base and its conjugate acid, or vice versa, then we can neglect it. And what that means is that the equilibrium concentration of the weak acid and its conjugate base is essentially the same as the initial concentrations, right? And so now we can write it like this. And now we have a very useful equation. This is called the Henderson-Hasselbalch equation. And it says that for a buffer solution, and this applies to a buffer solution where this condition is true, our x is a lot less than the initial concentrations, which we'll see. So it says that the pKa is equal to pH minus the log base 10 of the ratio of the concentration of the conjugate base to the concentration of the weak acid. So there it is once more, the Henderson-Hasselbalch equation. Write it down, memorize it, put it on your card, you'll use it. And when can you use it? So this is key to the next video we're going to talk when we talk about this. We talk about acid-base titrations. This is a very useful equation, and we can use it for a buffer solution when x is a lot less than the initial concentrations of the weak acid and its conjugate base. And you'll see how we can tell that in just a minute. So we're going to use this example to demonstrate the usefulness of the Henderson-Hasselbalch equation, as well as how you know if this condition is met, which most of the time it's met. So here we're going to calculate the pH of the solution. that's prepared by dissolving this many grams of lactic acid, which is a weak acid, and this many grams of sodium lactate, which is its conjugate base, in enough water so that we have a total of 750 mils of solution. And there's a Ka for lactic acid. And the way we're going to do this is we're going to solve this equation for the pH. Given the Ka, we can get the pKa. So I want you guys to work this out and come on back when you get an answer. Welcome back, guys. So we're going to calculate the moles of the lactic acid, which is this, and this is its molar mass. I just got it from the formula. So with this many moles of lactic acid, same thing for the sodium lactate. This is the formula, this is molar mass. Moles, the volume is 750 mils, so the concentrations are these numbers right here. So now that we know these, we can just pretty much plug into the Henderson-Hasselbalch equation. The Ka is 1.3 times 10 to the minus 4, so pKa is negative log base 10 of that, which is about 3.860. So that's our pKa, which goes here. We're solving for pH, so if I just, take this, rearrange it, solve for the pH, get pKa plus the log of the ratio of the base to the acid form. And there it is, there's the base, there's the acid form. I plug the molarities in here. Now real quick, because this is the same solution, the volume is the same for these, it actually cancels. We could have just taken the ratio of the moles in this case for this equation, and we would have got this. Try it, you'll get the same answer. Put these numbers in here instead of the 0.339 and 0.315, you get the same exact answer. So there's our pKa from here. There's our log of the ratio of the base to the acid, and we get the pH is 3.891. So the last thing here, guys, is how do we know that we could use the Henderson-Hasselbalch equation? Well, we know it's a buffer solution, so that's the first criteria, but was X a lot less than the initial concentrations? Well, X in this kind of calculation is the hydrogen ion concentration. So we know the pH, so we can get the hydrogen ion concentration by taking 10 to the minus pH, which gave us 1.29 times 10 to the minus 4th. And that's definitely a lot less, way less than 5% of the smaller of these two numbers, which is 0.316 or so. So yes, we could use the Henderson-Hasselbalch equation, and you're going to like it because when you can use the Henderson-Hasselbalch equation, buffer calculations become really simple. And that's all there is to that, guys.